to this section of circular motion part 2. Now we're talking about applications of centripetal and centrifugal forces. Today we're going to look at banking of curves on roads. We also call it super elevation. Now, centripetal force keeps a body moving along a curved path. Are we there? Right? Now this is a vehicle. It's going around a curved path. We require centripetal force to keep it moving in this cycle. A car traveling around a bend relies on the friction between the tires and the ground to keep it on the road. A racing car driver requires to go around at a much greater speed and hence greater acceleration. In most cases, the sideway friction is usually insufficient to provide the centripetal force required for the car to follow the curved track, and thus the tires slide sideways, a phenomenon known as skidding. Right? I have simulated to show a vehicle going around a curved track. Right? We require centripetal force to keep it in this cycle of latitude. Right? Now, if the car is a racing car and going around this bend, now if the centripetal force is not strong enough, the car will slip, a phenomenon known as skidding. Are we here? Skidding occurs when the frictional force between the tires and the road is insufficient to provide the centripetal force to keep the car on track. The vehicle fails to follow the curved track and the tires slide sideways. Construction engineers often bank road curves in order to reduce the chance of skidding or slipping of cars. Now look at it here. This is a car. I've just drawn this car to show you. Now the car is on a banked track at an angle theta. All right, this is the normal reaction of the tires on the road, and then this is the r sin theta, the force of friction pulling it inside. This is the road curves are constructed with a slope. Look at the slope towards the inward edge. The car, when moving along the curve, will appear slightly tilted to an observer, or as a result of the slanting or inclination of the track. Now, what will happen if there was no banking? All right? What will happen if there was no banking and the vehicle tries to round the bend at a high speed without leaning inwards? Simulate a force diagram, and this is the case where the motorcyclist was trying to go around the bend without tilting inwards. Now we have the normal reaction on the road, R is equal to mg. Now this is the case where the motorcyclist now, look at this case B, where he now slants at an angle theta. Are we there? This is the center of gravity acting at the center of his body. Now I projected the force down, which is equal to mg. Now this is his height, the height of the center of gravity above the road. Now this is the force of friction, which is equal to the centripetal force on him. I told you earlier, to keep a body constrained in the cycle of latitude, there must be a force on that body directed towards the center, which is F. Therefore, we can say F is equal to what? mv squared over r. mv squared all over r. Now this is the force, the centripetal force, multiplied by what? His height. Multiplied by h. That will give us what? mga, which is equal to mga. Now, this is mg times a, all right? Now, what will happen? If we multiply this, we can cancel out the m and n. So that will leave us with v squared all over what? rg, which is equal to what? a all over h, and which is equal to what? Tangent theta. All right? Tangent theta. Mark you, tangent theta is equal to opposite, which is a all over adjacent. This force, this formula is so important. Now here, we are what? V is equal to the speed of the car in meters per second. V is equal to the speed of car in what? In meters per second. Are we there? We are R. What is R? R is equal to what? The horizontal radius of the track in meters. Horizontal radius of the track in what? In meters. Are we there? And also, lastly, G. What is G? G is equal to acceleration due to gravity. Acceleration due to gravity. And lastly, the angle theta. Angle theta, tangent theta, angle theta is equal to the banking of the track. All right? Well, these are some of these calculations you need in civil engineering. We'll now go on to the calculations. We have an example. A car of mass 1,000 kilograms drives through a curved track at a speed of 200 kilometers per hour. If the reactions in the four wheels are normal to the track, and the horizontal radius of the track is 100 meters. Find 1, the angle of inclination of the track to the horizontal. II, the total reactions of the wheels. III, the centripetal force on the car. We have to take acceleration due to gravity as 10 meters per second squared. Now let us attempt to solve this problem. Now let's see. We have our data. Normally, we take our data. Let's see. Now we have our mass as 1,000 kilograms. M is equal to 1,000 kg. Are we there? And we have our velocity, V, as what? 200 kilometers per hour. 200 kilometers per hour. We convert this 200 kilometers per hour to meters per second, which will give us 55.6. 55.6 meters per second. What else we know? We know the radius of the track. R is equal to what? 100 meters. 100 meters. Now we are asked to what do we find? We are asked to find the angle of inclination of the track, which is theta, right? Theta is equal to, we want to know that. And then we are asked the reaction, that's II, the total reactions of the wheels. All right? Now, II, we have R is equal to. And then lastly, we have the centripetal force, III. F sub C is equal to. Now let's see. From our formula, we are able to derive V squared all over what? RG is equal to what? Tangent what? Tangent theta. The angle of inclination or the banking of the track. Are we there? Now, V squared is, our V is what? 55.6 squared. What is our R? Our R is 100. That's our radius. Right? Times. Right? What is our G? Our G is what? 10 meters. G is equal to 10 meters per second squared. So this will be multiplied by 10 is equal to what? Tangent theta. Alright? Tangent theta. Now if we evaluate this, we arrive at our theta is equal to 72 degrees. Therefore, theta is equal to 72 degrees. It's quite easy, right? Now let's go to II. Let's see. II. Right? In II, the axis, the reaction, look at it. The total reactions of the wheels. And now we know that R cos theta is equal to mg. R cos theta is equal to mg. Therefore, what is our R? R is equal to what? mg divided by what? Cos theta. Are we there? R is equal to, M is the mass, which is 1,000 kilograms, times the acceleration due to gravity, which is what? 10 meters per second squared, times what? 10 all over cos theta. What is our theta? Our theta is 72 degrees. Cos what? Cos 72 degrees. So when we evaluate this, what are we coming out with? We'll come out with 32.4 kilonewtons. 32.4 kilonewtons. That would be the reactions of the tires on the road. Then lastly, they asked us to find III, the centripetal force on the car. Therefore, we said the centripetal force is equal to what? mv squared all over r. And then our m, that's our mass. Our mass is 1,000 times the velocity. It was 200 kilometers per hour. We converted it to 55.6 meters per second. Therefore, we multiply it by v squared, 55.6 squared, divided by the radius. What is our radius? Our radius is 100. When you evaluate that, you get 30.99 kilonewtons.